Today, lesson 36C, properties of exponents. We could even think about it in terms of rules of exponents. And most of these ideas are things that you guys have already discovered on your own. And I told you when we started this whole thing, some of you were going to discover these things, and I was okay with you using them. I just wasn't going to mention them for about a week and a half. And so here we are. This is the day that we finally mentioned what the rules are. So, have you noticed a pattern when multiplying two expressions with the same base regarding or with regards to the exponents? Have you? What do you do with the exponents? You add them, exactly. So if the base is the same, we have the same base, and we're multiplying exponential expressions, we add the exponents. And so when we first started doing these, I would write it out like this, but clearly, if we add the two exponents, 3 and 2, that is the fastest way of getting to 4 to the 5th power. Same thing in this one. The fastest way is by adding the two exponents together. Remember, this is only true if the base is the same when we're multiplying exponential expressions. Okay? And then we jump to division. Have you noticed a pattern when dividing two expressions with the same base with regards to the exponents? You subtract them, exactly. So we started, and these are all problems from previous lessons, and I'm just showing you the way that we first did them. But if you simply take the top exponent and subtract the bottom exponent, that is the fastest way of getting to the fact that that simplifies to 5 to the 2nd power. Now remember, these rules only are applied if the base happens to be the same. Same thing in this one. The bases are the same, so if we subtract the exponents, we get to the fact that this is really negative 2 in parentheses to the 1st power. So when the bases, or when dividing like bases, keep the base the same and subtract the denominator exponent from the numerator exponent. In other words, numerator exponent minus denominator exponent. And then, have you noticed a pattern when having a power to a power with regards to the exponents? You multiply them, exactly. So when we did this problem originally, we got to the fact that this was 3 to the 8th power. However, the fastest way is by multiplying the two exponents together. And same thing in this one. This would end up being 7 to the 9th. All right, so when raising a base with a power to another power, keep the base the same and multiply the exponents. All right, but what happens if the exponents are negative? Well, the answer to that question is nothing. It's the same thing. It doesn't matter whether we have positive or negative exponents or fractional exponents, which, by the way, we will get to in another week or so. And so we know that the long way of getting to this answer, this is 2 to the 2nd power, but if you had added the exponent, you would have seen quickly that it is 2 to the 2nd power. And in the next problem, 4 to the negative 2 times 4 to the negative 5, the fast way of getting there, that is 4 to the negative 5 power. But remember, in math, we're not allowed to leave typically things with negative exponents. So 4 to the negative 5 became 1 over 4 to the 5th. What happens when we're dividing expressions with the same base and negative exponents? The answer is nothing. But the problem here for people who go too quickly with things like this is they make careless mistakes. Like the most common mistake is to say that this turns into 7 to the negative 3 power, 7 to the negative 15 power, which it's not negative 15. It is, I accidentally said the correct answer. It's 7 to the negative 3 power, which is then 1 over 7 to the 3rd power, because negative 9 minus negative 6 is negative 3. This is the long way of getting there. And there's another long way of getting there. But if you had subtracted exponents correctly, you would have gotten to 7 to the negative 3 very quickly, and then we would rewrite that as 1 over 7 to the 3rd. And the same thing when we have a power to a power. Just because we have negative exponents does not change anything that we do. We multiply the exponents. This is the long way of getting there. But using the rule or the property, we could have gotten to the fact that it is 6 to the 6th power much, much faster. Okay? So what happens if the bases are not the same? Well, sometimes there's a new rule that we can apply, and other times we can't. So if the bases are different and the exponents are different, don't make up some rule that does not exist. You know, doing something, you know, like that. I mean, you can't do that, right? Those two things are not the same. So in cases like that, in exponential form, 4 cubed times 2 squared is just 4 cubed times 2 squared. Now, there are some you could turn the base 4 into a base 2, but we'll come back to that another day. And same thing with this. Don't make up rules that don't exist, like that. You can't do that. The bases are not the same, so you can't subtract exponents. The same way you can't add exponents in the first one. So 5 cubed over 3 squared is just 5 cubed over 3 squared. Okay? All right, so let's put all of these rules together. So here are the basic rules that you already know. If 0 is an exponent and the base is not 0, that simplifies to 1. Now, we're going to talk in a minute about what happens if the base is 0. With negative exponents, remember x to the negative a power is 1 over x to the a, because typically we don't leave expressions with negative exponents. When we multiply exponents, we multiply with exponents, we add the exponents as long as the bases are the same. When we divide expressions with the same base and exponents, we subtract. And then when we have a power to a power, we multiply exponents. This is all already in your notes. But this extension, you can just sort of add this off to the side in your notes, because I think it's not in your notes. I'm calling this more exponent rules. So what if 0 is a base? So right next to, in your notes where it says 0 as an exponent, you can just write next to that, what if 0 is a base? Well, we have several scenarios. What if you had, and you don't have to write this down, but what if you had like 0 to the 5th power? What's that? 0. Okay. What if you had 0 to the negative 2 power? See, we have a little bit of confusion there, right? Somebody said 0. But remember, by the rule of negative exponents, technically this would be 1 over 0 squared. And 0 squared is 0. And from earlier in the year, what is 1 over 0? It's undefined, right? So in my open math, we would type in D&E for does not exist. So that is undefined. So 0 to the negative 2 power is undefined. So what we have is we have this rule that kind of works like this. That 0, and you should add this to your notes, 0 to the n power is equal to 0 for n being greater than 0. So if n is greater than 0, then 0 to the n power is 0. But what if n is less than or equal to 0? So if the exponent is 0, or negative 1, or negative 2, or negative 3.5, then it is undefined. And you will get some problems in the homework where you might have 0 to the 0, which is undefined. You might have 0 to the 2nd, which is 0. You might have 0 to the negative 3, which is undefined. Okay, so when the exponent is less than or equal to 0 and the base is 0, the answer is undefined. But if the exponent is larger than 0, then the answer is 0. All right? What about multiplying with exponents where the base is different, but the exponent is the same? And you should add this to your notes. So x to the a times y to the a equals x times y to the a means the base is different, but the exponent is the same. So something like this, and you probably should add that example so that it makes a little more sense to you. Notice that the bases are different, but the exponent is the same. So there is a rule for that. In a case like that, you would just multiply the bases and the exponent stays what it is. Okay? So 3 to the 4th times 5 to the 4th is 15 to the 4th, because 3 times 5 is 15. There's a rule for dividing with exponents where the base is different but the exponent is the same. Like x to the b over y to the b. Notice that the bases are different but the exponent is the same. So you would divide x divided by y all to the b power. So sometimes when you see it numerically it makes a little more sense. So if you had 16 to the 6th over 8 to the 6th, notice that the bases are different but the exponent is the same. So we can think of that as 16 over 8, all of that to the 6th power. 16 over 8 is 2, and so that is 2 to the 6th power. Okay? And then what if you have a power to a power with exponents? Like x to the a to the b power. Well, in a case like that, you have to work from the top down. So you would find a to the b power first, and then x would be to that power. So an example of that, 5 cubed squared. Notice that the 5 cubed is not in parentheses, so this is a different type of problem. So we would need to find 3 squared first, and 3 squared is 9. So 5 cubed squared simplifies to 5 to the 9th power. So we really have 4 new ideas here. They're not complicated, but they're 4 new ideas, extensions of exponents. Okay? So we're going to start with 1 through 6. And we're going to kind of take this in blocks of, probably in blocks of 3. So everybody quickly do 1 through 3. It does say in simplest exponential form. So that means you don't have to actually figure out what the answer is. So everybody try 1 through 3. Actually, just go ahead and do 1 through 6 because those 6 should go fairly quickly. 1 through 6. So now we get to start really talking about the rules and applying them. So when we are multiplying exponential expressions with the same base, we add the exponents. So that simplifies to 5 to the negative 1. But remember, unless we're told that it's okay to leave it like that, we can't leave things with negative exponents. In my open math, you're probably going to have to write that as 1 over 5 to the first. So just keep that in mind. When we are dividing exponential expressions with the same base, we subtract the exponents. So that ends up becoming 7 to the 4th. When we, once again, multiply expressions with the same base, we add exponents. So that turns into 6 to the negative 14th power. But we cannot leave it like that, so that should be 1 over 6 to the 14th. When we have a power to a power, we multiply exponents. So that turns into 3 to the negative 16, but we can't leave it like that. It should be 1 over 3 to the 16th. We add exponents in number 5. We've already talked about y, so that's 2 squared. And number 6, we got to pay a little more attention to what we're doing. We subtract the exponents. Top exponent minus the bottom exponent. The common mistake is to say that it's 5 to the negative 12. It's not 5 to the negative 12 because we're not adding exponents. We are subtracting exponents. Negative 5 minus negative 7 is positive 2. So that turns into 5 squared. Okay, let's go to number 7. Now here's where we start changing some problems. So let's just do these 3, and I think it's number 7 and number 8 that you're going to have to change. So just cross out your number 7 and change it to that. Cross out your number 8 and change it to that. I think your number 9 is the same. And then go ahead and write your answer in simplest exponential form, and I'll get back to you in about a minute. So in 7 and 8, we're applying a couple of these new rules that we just learned. So if the bases are different but the exponents are the same, we have one of those new rules. So we should think of it like this. 2 over 8 simplifies to 1/4. So you could either write it as 1/4 in parentheses to the 4th or 1 over 4 to the 4th. My open math would take either version there. And remember, in number 8, don't get this new idea mixed up with this. This is totally different than this. So don't get them mixed up. Okay? So we have to start from the top down. So we have to do 2 cubed first. 2 cubed is 8. And so that simplifies to 5 to the 8th. And then number 9 is one of the previous rules. So we subtract exponents when the base is the same. and we are dividing exponential expressions. So negative 4 minus 4 is negative 8. That's 3 to the negative 8, but of course we cannot leave it like that. That is 1 over 3 to the 8th. All right. In 10, 11, and 12, I think perhaps all three of those are different. So you'll have to change your number 10 to that, your number 11 to that, and your number 12 to that. And I'll get back to you in a minute. So number 10 applies one of these new rules. Yes, the bases are different, but the exponents are the same. So we apply that rule. And 25 over 5 is 5, so we end up with 5 to the negative 2. But remember, we can't leave it like that. 5 to the negative 2. I guess I should have left that as 1 over 5 squared. I'll have to change that. Yeah, I should have left it as 1 over 5 squared because it does say simplest exponential form. In number 11, we're applying, once again, one of the new rules. The bases are different, but the exponents are the same. So we'll utilize that rule. So that should be 21 to the 5th. And when 0 is a base and the exponent is less than or equal to 0, the answer, of course, is undefined. In MyOpenMath, we type in D and E to represent does not exist. Okay? All right, continuing on. Number 13. So sometimes we've got a fraction where we need to do some simplifying before we can do the overall simplification. So to me, this is no different than an order of operations problem, where if you can simplify within the numerator or denominator, you should. So here's what I'm saying. What I would be doing is I would apply the rule to multiplying expressions with the same base there to simplify the denominator. And that becomes 2 to the 8th, and then we can simplify that to 1 over 2 to the 4th power. So the next block of problems, that's exactly what we are doing. So I would like you, that was number 13. So I would like you to go ahead and do through number 18, and then we'll compare those. So go ahead and do 14 through 18. So we're simply following the order of operations. In number 14, we should simplify within the numerator first. 4 to the negative 5 times 4 to the 8th is 4 to the 3rd. So now we have 4 to the 3rd over 4 to the 3rd, which of course is 1 for several different reasons. Number 15, we should simplify within the parentheses first before we deal with that outside exponent. We don't have to do that, but we really should always follow the order of operations. So within the parentheses, you should deal with that 6 to the negative 3 times 6 to the 5th. So we would add those exponents. So within the parentheses, so far that simplifies to 6 to the 4th over 6 to the 2nd by simplifying the denominator. And then 6 to the 4th over 6 to the 2nd is 6 to the 2nd. So now we end up with 6 to the 2nd to the 2nd, which is, of course, 6 to the 4th. Just following the order of operations. Number 16, we should really deal with this part right here first, because we have a power to a power. And so that gives us in the numerator 2 to the 2nd times 2 to the 6th over 2 to the 2nd. So now simplifying the numerator, we end up with 2 to the 8th over 2 to the 2nd, and that simplifies to 2 to the 6th. Number 17, we should simplify the denominator first. And so that is 3 to the 2nd, as far as or 3 to the 3rd, excuse me. So we end up with 3 to the 5th over 3 to the 3rd, and that is 3 to the 2nd. And then in number 18, we should simplify the numerator, then simplify the denominator. So the numerator becomes 3 to the 6th. The denominator becomes 3 to the negative 8, because 3 to the negative 4 times 3 to the negative 4 is 3 to the negative 8 by adding the exponents. And then when we are dividing expressions with the same base, we subtract exponents. 6 minus negative 8 is 14. So that simplifies to 3 to the 14th. All right, go ahead and finish the rest of the problems in the lesson. So 19 through 22. Follow the order of operations and apply all the exponent rules that you know. Number 19, we should simplify within the numerator and then also the denominator. So in the numerator, we end up with 5 to the negative 8. In the denominator, we end up with 5 to the 0 because we add exponents. And then if we subtract exponents, which I don't know that we necessarily need to in that one because the denominator is 1, but we end up with 5 to the negative 8. But we can't leave it like that. That turns into 1 over 5 to the 8th. Or 1/5 in parentheses to the 8th would be okay as well. Number 20, simplify within the numerator. So we have a couple of things where we have a power to a power. So the first part turns into 2 to the 0. The second part turns into 2 to the 6th. So now we have 2 to the 0 times 2 to the 6th over 2 to the 2nd. Add the exponents in the numerator. So we end up with 2 to the 6th over 2 to the 2nd, which turns into 2 to the 4th. Number 21. Now notice we have different bases here. So therefore, the answer is 3 cubed times 2 squared times 5 to the 6th. Now if we had the same exponent somewhere along the line, we could have done something with that, but we don't. Bases are different, and all the exponents are different. In number 22, simplify within the parentheses first, so simplify the numerator. So that numerator turns into 7 to the negative 5, so now we have 7 to the negative 5 over 7 to the negative 3, all of that to the 4th. So within the parentheses, subtract exponents. So we end up with 7 to the negative 2, all of that to the 4th. Now we have a power to a power, so multiply exponents, and then turn that into either 1 over 7 to the 8th or 1/7 in parentheses to the 8th. All right, we are finished. You know we're